This is our third lesson in our series on the lithosphere. I'm sure by now you're getting a good idea of the importance of the resources that the Earth's lithosphere produces and how we use them. In this lesson, we'll be focusing on the mining and processing of minerals containing iron and phosphates. Before we start this lesson, look around you for a moment. List all the objects you can think of that are made of iron. Here's a clue. Everything that is made from steel or stainless steel contains iron. The bodies of cars, frames of bicycles, doorknobs and locks, pots and pans, knives, reinforcements for cement, and building equipment are a few examples of how extensively iron is used. By the end of this lesson, you should be able to describe open pit mining, explain using equations, iron and phosphate extraction, and investigate the effect the amount of fertilizer used has on plant growth. As you can see from this list, iron is the fourth most abundant element of the lithosphere. One of the characteristics of iron is that the pure metal reacts quickly with other elements, especially oxygen. We find iron as a variety of different compounds in rock. The most common iron compounds are hematite, which is Fe2O3, magnetite, which is Fe3O4, and siderite, which is FeCO3. South Africa's reserves of iron ore are 9,300 megatons. These are the sixth largest reserves in the world, and we export most of our iron ore. The major iron deposits are found in the Northern Cape at Sishen. The ore mined here is transported via rail to Saldanha Bay, 800 kilometers away from where it is exported. High-grade deposits of hematite are also mined at Tabazimbi. Metal Steel is the company that both mines the ore for export and is involved in changing it into steel for local use. Now, let's start at the very beginning, when people first discovered iron, and look at their techniques for extracting it from its ore. To give us a bit of a history of how we learned to work with iron is Dr. Tom Hoffman from Wits University.
Hi, I'm Tom Huffman, the professor of archaeology at Wits. My specialty is the last 2,000 years. Now, archaeologists call that the Iron Age because one of the principal technological features of that time was the ability of people to smelt iron and make things out of it. This picture shows you what iron smelters look like or did in the recent past. They're great big ovens. What I want to do now is show you how all of this works. First of all, you start off with a rock, the iron ore. People go out and find it in the right places. They break it up, they put it inside the furnace. Now I'm going to refer to this one. This is a replica of a copper furnace, but the copper and iron work very similar. You would take the iron, break it up, or the copper, break it up, put it inside with charcoal. And you'd have iron ore, charcoal, iron ore, and stuff like that built up. In this case, it's open, but as you remember from this picture, the ovens are closed over. Being closed means you can create a reducing atmosphere. And what they want to do is get the temperatures up to something like 1,500 degrees centigrade. And they would do it by using billows. This is 1/2 of a billow. The billow operator would have 2 of these. He sticks them into the end of this blowpipe. The blowpipe goes into the furnace. And so where the blowpipes are, that's the hottest part of the furnace. And what we're trying to do here, by going up and down, making it full of air, then pushing the air in, you lift one up as you push the other one down, you go back and forth. This can take several hours, by the way, and you would have alternating guys doing this. You get the temperature so hot that the junk in the ore melts away. You're not trying to melt the ore because that would then create cast iron and you can't work it. So what you're doing is getting the silica, just like sand grains, you're getting the silica out and you create what's called slag. obviously they didn't want this. They threw this away. They were looking for bigger chunks that had a lot of iron in them. They take that iron and go to a smithy area. Now that's just where you've got a hearth on the outside. You still have billows because you want to get it fairly hot, but now it's an oxidizing atmosphere and it doesn't have the same chemical, physical bit. And what you're doing is to get it hot enough that you can hammer it, and you're breaking away all the bits of slag you don't want, making it into something. Generally speaking, they want to make hoes. This is an ancient hoe. This is a piece of wrought iron. Let's make sure we know the difference between this and cast iron. If you look closely, you can see the little dimples on here. This is where the blacksmith used a hammer to pound out the iron, it's called a bloom, the iron bloom into this shape. If this was cast iron, you wouldn't see any of that because the iron would have been poured in a molten state into a mold, allowed to cool, and then you've got this rigid form which you can then put hot things onto and stuff like that. Now this would go on the end of a stick like that, and a woman would use this to hoe in the ground to plant the seeds of sorghum and millets, the African crops that they had. Well, some of you may wonder where this started. And to understand the history of this, we've got to go to the Near East, where people in Turkey in particular, everybody in that area was doing copper and bronze. But the people in Turkey at about 1800 BC, that's a long time ago, 1800 BC, they were experimenting with iron. They already knew how to do this part, the copper. Now what they had to do was put a top to it and get it higher in a reducing atmosphere. They learned to do that, and they started the whole iron smelting industry. It spread from there to Egypt, and then later on caravan routes that went right across North Africa. They came down into West Africa, introduced it to all the populations there, and at about 500 BC, everybody in that area became competent in smelting. So when our first black farmers moved down here, they already knew all about this.
Today, iron ore is taken out of the ground by open pit mining. The surface of the ground is removed using huge machines to expose the iron ore beneath. This often happens over a very large area. The ore is blasted out using explosives. As you can see from these photos, the open pit mining removes the soil and destroys the vegetation. Open pit mining completely destroys the beauty of the environment. However, on some mines there are plans to fill in the pits after mining operations are completed and to restore the land to its original condition. Let's move on to the next step in the process. How do we get the iron out of the rock? The ore must be refined. It is crushed and sorted into grades. The best grades of ore contain more than 60% iron. The crushed ore is washed so that the sand and clay can be removed. The iron ore is separated further from unwanted substances using magnets. You've probably played with magnets and seen how iron displays very strong magnetic properties. So when it comes to drawing out the iron, this separating method is ideal. Next, the iron ore is formed into pellets and sent to a blast furnace for sintering. A blast furnace is a huge tower-shaped structure. It's made of steel and is lined with heat-resistant bricks. The iron ore is fed into the top along with lime and coke. What are coke and lime? Well, we're not talking about drinks. Coke is coal that has been heated until it is almost pure carbon, and lime is calcium carbonate. Now let's check on what happens inside the blast furnace. Hot air is blown into the furnace to burn the coke. The carbon is oxidized to form carbon dioxide. This is an exothermic reaction. The heat energy of this reaction pushes up the temperature to over 1000 degrees Celsius. The carbon dioxide reacts with more coke to form carbon monoxide. The carbon monoxide is what's really important. This gas removes the oxygen from the iron oxide, actually reducing it from iron 3 plus to iron. At such high temperatures, the iron is molten and so is free to flow down to the bottom of the blast furnace. When iron oxide is reduced, then the carbon monoxide is oxidized. Can you use these two half reactions to write an overall redox reaction? The number of electrons lost and gained must be the same. The lowest common multiple of 2 and 3 is 6. So we multiply the reduction half reaction by 2 and the oxidation half reaction by 3. Next, we add these two half reactions together to get the overall reaction. But this is not the only reaction taking place in the blast furnace. The original iron ore also contains mineral impurities such as silica containing silicon dioxide. Silicon dioxide reacts with a calcium carbonate to form a molten slag of calcium silicon oxide and carbon dioxide. The molten slag is less dense than the molten iron. Think about this for a moment. If the molten slag is less dense than the molten iron, where do you think the slag will be found within the mixture of liquids? Well, because the slag is less dense than the iron, it forms a layer above the liquid iron. Each layer is drained separately from the furnace. The iron is then cast into pig iron ingots. This iron is very hard but brittle because of the large carbon content from the coke. The pig iron can be further refined in a furnace where it is converted into steel alloys. So what is an alloy? Iron is often mixed with other elements such as carbon and transition elements such as nickel and manganese to form alloys of iron. The alloys of iron have different physical properties compared to pure iron. For example, steel is an alloy of iron and is stronger, more flexible, and more resistant to rust than pure iron. The waste products from the iron extraction process include slag and a variety of poisonous gases. Slag is used to fill quarries or to build roads, but most of the gases are released into the atmosphere. Now, for the second part of our lesson, we're going to turn our attention to the mining of phosphates. Phosphates are oxides of phosphorus and are made from phosphoric acid. We will show how rocks containing naturally occurring phosphate minerals are mined, how the minerals are extracted, processed, and used to make phosphoric acid. Phosphoric acid can be used to make a variety of other products. One of the main uses of phosphoric acid is to make fertilizer. Fertilizers are very important for agriculture because the phosphate used up from the soil by plants needs to be replenished. In South Africa, our main source of minerals containing phosphates is near Phalaborwa in Limpopo province. This mine is the largest producer of phosphate rock in the southern hemisphere. The method of mining phosphate rock is similar to that of iron ore. An open pit mine is excavated using heavy machinery called draglines. The dragline bucket is large enough to hold a van. It scoops up the ground above the phosphate rock called the overburden. Overburden is the term used for the earth above the ore to be mined or excavated. The overburden is dumped in spoil piles on the side of the pit. The dragline then digs out a mixture of phosphate rock, clay, and sand. Water is added to the mixture to create a slurry. The components of the mixture, sand, clay, and phosphate rock, have different densities and can be separated by flotation. The clay slurry is pumped into a settling pond. The sand is used for filling in quarries. The phosphate rock is sent to a chemical processing plant. The phosphate-bearing rock from Phalaborwa contains a mineral called fluorapatite. This is the mineral that is extracted. The phosphate rock is railed 800 kilometers to Richards Bay, where it is processed to extract the mineral. Let's have a look at this extraction process. Sulfuric acid is reacted with a phosphate rock. The products of this reaction are phosphoric acid and calcium sulfate, also called gypsum. The two are separated by filtration and the gypsum is discharged. The phosphoric acid is concentrated by evaporation in a vacuum. It's then sold to fertilizer producers in South Africa and overseas. At Richards Bay, there is also a fertilizer plant. Here, the phosphoric acid is neutralized with ammonia gas in a large closed container called a reactor. The resulting sludge containing ammonium phosphate is pumped into a drum granulator so that it can be worked into small, regularly sized spheres. This granulation process is intricate and needs extra ingredients called binging and coating agents. The granules are finely dried and bagged. There's a lot of debate around the appropriate use of fertilizers. There are some people who strongly believe that only organic farming methods should be used, while others believe that fertilizers are essential for solving the food requirements of Africa. Some people say that any use of phosphate-based fertilizers leads to the pollution of rivers, while others believe that if the correct amounts of phosphates are provided for plants, they will use what is there and there will be no excess to be washed into the streams and rivers. For your task today, let's do a practical investigation. Plan and carry out an investigation to test the effect of using different amounts of phosphate fertilizer on the growth of bean or pumpkin seedlings. Remember to make sure your investigation is a fair test and that you collect accurate data to make conclusions. Be prepared to give a presentation on your investigation. That is all for this lesson, but join me for our next lesson when we will explore the mining and processing of fossil fuels.
Yeah.